Welcome to this journey across mathematics, geometry, and the hidden architecture of truth, and their profound role in physics, engineering, and the real world. It is a PESEL research exploration inspired by works such as the book Nature of Mathematics by Ian Stewart and lectures by professors of mathematical physics who emphasize that algebra is not just symbolic manipulation but a language for decoding reality. 2. The uninitiated, the term quadratic is confusing. The prefix quad usually denotes the number 4, as in quadrilateral or quadruple. However, a quadratic equation is defined by a variable raised to the power of 2. The resolution to this linguistic puzzle lies in Latin. The word stems from quadratus, meaning square. In the geometric tradition of mathematics, x square is not merely a variable, multiplied by itself. It represents the area of a literal square with sides a length x. Thus, a quadratic equation is quite literally a square-like equation. When we solve the quadratic equation, we are investigating the properties of areas and the side lengths that generate them. Before diving into solutions, we must clarify the objects we are manipulating. In formal analysis, an expression and an equation serve two entirely different logical functions. An expression is a mathematical phrase. A quadratic expression, such as ax squared plus bx plus c, is not a sentence. It represents a value that changes depending on the input x. It defines a function or a mapping. When we look at the expression, we are interested in its behavior. Where is it increasing? What is its curvature, the second derivative? 2a. The expression is a landscape. It exists everywhere simultaneously. An equation is a mathematical sentence or a constraint. By setting the expression equal to a specific value, usually 0, we are no longer looking at the whole landscape. Instead, we are asking a specific question. At which precise points does this landscape cross the sea level? When we convert an expression into an equation, we impose a constraint. According to mathematician Terence Dow, an equation is a statement that demands truth at specific points. Setting x squared plus bx plus c equal to 0 collapses the infinite landscape into a search for precise coordinates where the curve touches the horizon. These points are the roots. They are not arbitrary. They are the exact locations where the system satisfies the condition. This shift from expression to equation marks a philosophical transition. We move from observing behavior to extracting truth. Solving a quadratic equation is an act of inversion, a way of uncovering hidden structure within the landscape. Geometric interpretation. To solve x squared plus 10x equal to 39, we can draw a square of side x to represent 10x. We can add 4 rectangles of dimension x by 2.5 to each side of the square. This created a cross shape. To complete the large square, we can fill in the 4 corners. Each corner was a small square of 2.5 by 2.5. By adding these areas, we can bridge the gap between a visual shape and a numerical solution. 2. When we move from the ancient area problems to Cartesian geometry, the quadratic expression fx equals ax squared plus bx plus c reveals itself as the parabola. The squareness of the equation creates a specific type of symmetry. Unlike a linear equation, which has a constant rate of change, the quadratic has a linear rate of change. The first derivative of fx equals to ax plus b. This means the slope changes at a constant rate, leading to the elegant, U-shaped curve. Think mathematics. A root or solution is a value for that makes the equation true. If we view the quadratic expression fx equals ax squared plus bx plus c as a physical landscape, the roots are the latitudes where the elevation is exactly 0. The 3 types of definitions of root is as follows. Algebraic definition. A number r is a root if a squared plus br plus c equals 0. Now the geometric definition. The roots are the x-coordinates of the points where the parabola intersects the x-axis. Next, the multiplicity. A quadratic equation always has exactly 2 roots, as mandated by the fundamental theorem of algebra. Though they may be identical, a double root, or exist only in the complex plane. Factoring. is the most elegant method for solving a quadratic. When x squared plus bx plus c can be rewritten as left parenthesis x minus r1, right parenthesis left parenthesis x minus r2, right parenthesis, the roots become immediately visible. According to algebraic theory, this method relies on the zero product property. If a product equals 0, one of the factors must be 0. This approach is efficient when the relationship between the coefficients is simple. It is the mathematician's shortcut, a way of revealing structure without heavy computation. Factoring teaches us to look for patterns, symmetry, and hidden relationships. 2. Completing the square is the most honest method of solving a quadratic. According to classical geometry, this technique dates back to the Greeks, who literally rearranged shapes to form perfect squares. Algebraically, we add b squared over 4a to both sides to create a perfect square trinomial. This reduces the equation to left parenthesis x plus b over 2, a right parenthesis squared equals something. Now the variable appears only once, allowing us to take the square root. This method reveals the geometric heart of the quadratic. It shows that every quadratic can be reshaped into a square, a profound insight into mathematical structure. It is the generalization of completing the square applied to the coefficients a, b, and c. According to the book Algebra by Israel Gelfand, the formula is a universal algorithm that guarantees a solution regardless of the numbers involved. Whether the coefficients are integers, decimals, or complex values, the formula extracts the roots with precision. It is a black box that always works. This universality is why the quadratic formula is one of the most recognized equations in mathematics. It represents the triumph of general reasoning over specific cases, for ruled applications, where coefficients are derived from noisy data. We use iterative algorithms like Newton-Raphson. This method starts with a guess and walks down the slope of the parabola until it hits the 0 point. In modern physics and data science, we often solve quadratics using numerical methods, such as Newton's method. According to computational mathematics, this technique uses the derivative to refine an initial guess. We start with x0 and compute x1 equals x0 minus f of x0 divided by f prime of x0. This iterative process walks us toward the root. It reflects the reality that many equations in science cannot be solved exactly. Instead, we approximate. Numerical iteration teaches us that solving is not always symbolic. Sometimes it is a journey of refinement. A root is more than an answer. It is a zero of the function. According to advanced calculus, roots represent the points where the output of the function becomes 0. For a quadratic, there are always two roots when counted with multiplicity. These roots tell a story about the system. They reveal where the curve crosses the horizon. They define the boundaries of behavior. They are the anchors of the parabola. Understanding roots is essential for interpreting the meaning of the equation. The significance of roots. Why do we care about these specific numbers? In a professional context, roots represent critical transitions. Firstly, the break-even point. In economics, if FX represents profit, the roots are the exact production levels where the company stops losing money and starts making it. Secondly, equilibrium. In physics, roots often represent points of stability or the exact moment an object returns to its baseline, for example, when a projectile hits the ground. Thirdly, resonance. In electrical engineering, roots of quadratic descriptors tell us the frequencies at which a circuit will resonate or fail. Fourthly, the nature of reality. The existence of roots tells us if a solution is physically possible. If the roots are complex, d0, it often indicates that the system, as defined, will never reach the state we are asking for. For example, a ball will never reach a certain height given its initial velocity. Distinct real roots. When the discriminant b squared minus 4ac is positive, the quadratic has two distinct real roots. According to algebraic geometry, this means the parabola intersects the x-axis at two different locations. These roots represent two unique states where the condition is satisfied. In physical systems, this often corresponds to two possible times, two possible positions, or two possible configurations. Distinct real roots indicate diversity in the solutions. They show that the system has multiple valid outcomes. Repeated real root. When the discriminant equals 0, the quadratic has a repeated real root. The parabola does not cross the axis. It kisses it. According to Professor Ian Stewart, this is a point of perfect balance. The system has collapsed into a single critical state. In physics, this often represents equilibrium. In engineering, it may indicate a threshold between stability and instability. The repeated root is a moment of symmetry, a point where the system is delicately poised. Complex roots. When the discriminant is negative, the quadratic has complex roots. These roots do not lie on the real number line. They exist in the complex plane. According to complex analysis, this means the parabola never touches the horizon. In physical terms, this often indicates that the desired condition is impossible under real-world constraints. Complex roots are not failures. They are signals. They tell us that the system behaves in a way that cannot be captured by real numbers alone. Sure. Thank you for joining me on this exploration of the quadratic equation. Its origins, its geometry, and its profound significance across mathematics, physics, engineering, economics, and the natural world. It is a doorway into understanding how the universe behaves. I hope this journey helped you see the beauty, symmetry, and power hidden within this simple yet extraordinary mathematical structure. If you enjoyed this video and want to continue exploring the deeper connections between mathematics and the cosmos, please consider subscribing to the channel. Your support helps me create more research-driven content that blends scientific depth with cinematic storytelling. Thank you again for watching, and I look forward to seeing you in the next episode.